All right, week 12. So in this chapter, we're going to focus on electrons that transfer in chemical reactions. So this is important because really 4 of our 5 reactions from week 10 undergo this kind of electron transfer, this electrochemistry. So I'm going to show you how to oxidize and reduce. This is going to be based on their oxidation states. We have to start learning about batteries and how they can transfer electrons to some of our devices. We're also going to look at the activity series to determine if reactions or batteries would be working batteries. And then we'll apply this to corrosion and oxidation processes at the end. So one of the major features of this chapter is to understand that our body is made of electricity. We saw that in our last chapter with electrolytes. So how do we get electricity from other molecules? By eating them, by transferring their electrons from sugar molecules to our bodies. So this is the way that we're going to see the flow of electrons, just like the flow of water through a water hose. We need to figure out who is giving the electrons and who is taking them. And that will apply to a lot of other courses like biology and specifically physiology, if you take those later. So you can imagine that electricity is created in all kinds of different ways. You can create electricity in power plants. This is usually with copper turbines spinning really fast around some magnets, and those magnets can generate those electrons and send them through wires to your house. You can also imagine that this happens in the mitochondrion of all of our cells. These are the power plants of our cells. They do electron transport through lots of different biological cycles, producing ATP, as you'll probably learn in biology or may have already. It also happens in the plants. These kind of green pigments in a lot of plants can absorb the sunlight, transfer that into chemical energy through this electron transfer process. And then lastly, you'll understand in this course, in this chapter specifically, that electrons released by atoms and compounds and batteries are other ways to see chemical reactions as a way to produce electricity. So when we think of chemical electricity, we have to think of atoms that give up their electrons to be like noble gases. This could also be done in reverse. That would be the major difference between a combination and decomposition reaction from back in week 10. You can look at the example like this, where hydrogen and chlorine, they have no charge. So this is elemental hydrogen with no charge. This is elemental chlorine with no charge. But notice as hydrogen gas becomes the hydrogen ion, it becomes a +1. So in order to become a +1, it has to give up one of its electrons. And then chlorine, going from 0 to now -1, must have accepted those electrons from hydrogen. And this has to happen twice because there are 2 atoms each. There is no H2Cl2. It's a perfect one-to-one kind of relationship between hydrogen ions and chloride ions. It's a monoprotic acid in this case, if you remember back from our last chapter. So it's important to realize that hydrogen had electrons that it gave up. That loss of electrons will be called oxidation. And chlorine gained electrons. That gain of electrons is reduction. We'll see that a lot later on in this chapter. But this is a recognition of we're transferring electrons, just like we're transferring electrons from a power plant to our house. This is just using atoms in a beaker or in a test tube rather than a fancy turbine with fancy magnets. One of the easiest ways to recognize changes in oxidation, changes in reduction processes, is to realize where an atom starts and where it finishes. So in the reactants, it has a specific oxidation state, kind of like a charge. Charge is really a leftover kind of concept where you have extra electrons as a result of some kind of reaction. But in a way, oxidation state is like the charge inside the molecule that adds up to be the overall charge. So oxidation state, almost synonymous with charge, but it's not exactly charge. It's just, it's going to look like it when we put it into, that upper kind of right corner as we'd seen it earlier in the semester. In order to do this safely, we're going to look at electronegativities and realize that the more electronegative you are, the more likely you are to own the electrons that are in that chemical bond. So this is specific to covalent compounds, because in ionic compounds you can already see their charge and just assume that their charge is their oxidation state. So as you look at an example like water, think about who's the biggest bully. When you think about who's the biggest bully, you can think, well, oxygen is second biggest in the entire table, even though it starts with 6 because of its position in group 16, that's 6 valence electrons. So if oxygen starts with 6 electrons, notice here, it's going to have all 8. So even though this electron was technically belonging to hydrogen, and so is this one, because of the electronegativity of oxygen based on hydrogen electronegativity is 2.1, oxygen is 3.5, and that's enough to say that oxygen is going to get what it wants. So if it has 6 electrons and it goes to 8 electrons, notice it has 2 more than it started with. So if it has 2 more electrons than it started with, it's going to be a -2. So it's 6, now has 8. It's going to have that -2 charge, because it has 2 extra negative electrons that it didn't previously have until it bullied them away from hydrogen. And that's what we're after in this situation, because now hydrogen started with 1 electron. It's in group 1 of the periodic table. And now it ends up with 0 electrons in the end, and that's going to make it feel positive. And we'd expect hydrogen to feel positive just like all the alkali metals below it. So really these ideas of oxygen feels as if it's -2, we'd expect that if it were with a metal anyway. And seeing hydrogen as a +1, we'd expect that as an acid anyway. So neither one of these ideas should be too brand new, because they're really just saying that even though they're sharing electrons, they're not really sharing very well. And that's the idea behind electron bookkeeping. So as you assign electrons, just remember to use electronegativity. Give the most electronegative atom all the electrons at once, which is typically an octet. Hydrogen's never going to be a bully in any situation that we see in introchem, so you're never worried about that duet rule with it in helium. So really just give the bullies 8, the second biggest bully whatever's left, and the third biggest bully whatever's left, and then whoever's left gets probably nothing in the end. So as you saw in this example here, oxygen had 6, but it ended up with 8. Because of its electronegativity of 3.5, which is second highest only to fluorine at 4.0, oxygen essentially gained 2 electrons. That's not really the case. It's still sharing, just not very well. But it's owning those electrons more so than hydrogen ever will. And that's why we say an oxidation state of -2. Hydrogen had 1 electron, but it ended up with no electrons in the end because of its low electronegativity of 2.1, and that resulted in a +1 charge because it still has 1 positive proton, but now with no negative electrons left. So this difference of, we had 6, we now have 8, 6 minus 8 is -2. We had 1, now we have none, that's a +1. So that's another way to mathematically think about what happened. But really this idea that electrons are negative, you're adding negative to your charge, and if you're taking away negative, your positive is still there because of your protons. It's no different than what we did in exam 1 and 2. So let's look at another example. Here we have NH2F. So based on Lewis dot structure ideas from exam 2, hopefully you would think nitrogen in the center. Hydrogens and halogens can't really be center atoms because they can only share once. We have nitrogen with 5 valence electrons because it's in group 15. We have hydrogen with 1, we have hydrogen with 1 because they're in group 1. And then we have fluorine with 7, they're in group 17. And then we connect those single dots just like exam 2. So now we're going to look at electronegativities. Electronegativities tell us that fluorine is the biggest bully at 4.0. Nitrogen tied for third with 3.0 with chlorine. Chlorine again being a larger atom, that electronegativity means less, so it's not a hydrogen bonder like we saw back in exam 3. Hydrogen's down at 2.1. So now that we see the electronegativities, we'll get the electronegativity table on all exams and homeworks and so forth. Now we have to realize that chlorine is the biggest bully. If chlorine's the biggest bully, that means it's going to get all the electrons that it ever wanted, which is all 8. So even though it had 7, it's gaining, in a sense, gaining this electron here from nitrogen. So if it has 7 and now it has 8, 7 minus 8 is a negative 1. Again, electrons are negative, and if you're gaining 1, you're going to become negative, and that's what we just saw here with fluorine. And we'd expect that for fluorine because fluorine's always been a negative 1 and probably will always be a negative 1 because there's nobody to bully it. The disadvantage of what we have next is nitrogen is second biggest bully, and that means it's going to get what's left over. So even though it started with 5, it's going to end up with everything that fluorine did not take. So because of its 3.0 electronegativity, it's second to fluorine at 4.0, it's going to get what's left over. And notice what's left over is 1, 2, 3, 4, 5, 6. So nitrogen started with 5, it ends up with 6, that's a negative 1 also. We've never seen nitrogen with a negative 1. And the reality from that is because we've kind of lied to you for a very long time. We told you what was easier to think about, and that's that nonmetals are going to go to their nearest noble gas, and that's true most of the time. Unfortunately, nonmetals will do whatever they have to. Sometimes life gives you lemons, and sometimes it gives you lemonades, and here, nitrogen's getting some lemons. It's not getting what it wants. Your parents may have told you, you get what you get and you don't throw a fit, so nitrogen here gets 1 extra. That's closer to being a noble gas, but it's never going to get there because it's being bullied by fluorine in this case. What's left over in this process is we see that hydrogens are left over, and these hydrogen atoms out here with 2.1, they had 1, ended up with 0, so they're positive 1. Over here, we ended up with 0, so we had 1, ended up with 0, that's a positive 1. So if we add all those together, notice if in the formula NH2F, we have hydrogens at positive 1, so that's a positive 1 times 2, so that's a plus 2 total. We have nitrogen as a negative 1, and we have fluorine as a negative 1, as we always expect it to be. So 2 negatives and 2 positives make 0, and we notice that this overall compound was 0. And that's the idea behind oxidation states and this electron bookkeeping method, making sure that your overall charge equals the sum of your oxidation states, and that's what we just proved in this example here. The disadvantage of what we want to watch out for is if we traditionally thought of NH2F, we may think that fluorine is a negative 1 like it always was. We might think nitrogen, like nitride, is a negative 3 like it's always been. And then hydrogens are going to be 2 positive 1s as they've always been. So 2 of those things were held true. But now we notice that for the first time, this negative 3 is not what nitrogen gets. It ends up being a negative 1 instead, and that's because for the first time ever, we've drawn an example where we've put a bigger bully than nitrogen with it, and there isn't too many atoms that can do that, oxygen and fluorine being the only 2. So those traditional charges may not work. So we're going to have to identify those charges through this kind of method, or the shortcut that we'll teach you a little bit later. So in this case, fluorine -1, nitrogen -1, both hydrogens a +1, and that's what happens when you get bullied. Sometimes you get what's left over and not what you want. So as you look at oxidation states, there's lots of examples of this. You can imagine that you can kind of do this in your head to some small degree. If you imagine 2 oxygens, that's a -4, then you need a +4 in order to balance it. If you have a -2, you need a +2 to balance it. If you're by yourself, you have to, you're not sharing any electrons, so you're going to be perfectly elemental, which is always going to be 0. If you have 4 positive ones, notice you're going to be equal but opposite. Elemental hydrogen, elemental chlorine, so they're sharing equally with themselves. They're not going to gain or lose anything. Here's a perfect match between positive and negative, like we've seen before in our last chapter even. Here we have a positive-negative, perfect match again. Here we have, notice, a +1, a -8, and that +7 has to be what's missing. So pretty creative to see such a high charge for transition metal. But if you count back 7 spaces, you can see why manganese would want to do that. It's going to be noble gas-like if it does. Here with zinc and oxygen, perfect match, +2, -2. We could imagine here we could reverse these charges to see where that 1 and that 2 came from. That still holds true. As you look at other examples, you might see something pretty weird here. You have hydrogen peroxide where you're going to have a -1 on each oxygen. So that one's pretty unique based on that idea. In this case, the peroxide anion. Here, peroxide itself with 2 hydrogens. You're going to be a -1 on each oxygen. So we're not really going to see examples like this peroxy anion in our class, but we will see something like peroxide where oxygen does have to share with itself, so it's not going to get quite to that -2 like we'd expect. A more traditional -2 +1 that we'd expect, again, this is +2 total, so oxygen has to be an equal match at -2. And again, we probably won't see any of these weird oxidations of oxygen because we don't just see those in introchem at all. But in this case, we do have bullies, so oxygen may be something that it's not. But again, we won't see examples like that in introchem. That just gives you kind of a taste of what to expect and what to see. You should always be able to kind of check your work. If you go back and plug your charges in, you can kind of see what needs to be a charge, or what, in this case, what needs to be an oxidation state, an oxidation number, in order to make the overall charge, in all of these cases, 0. So as we look at oxidation states, just remember that if you own fewer electrons than you started, you're going to become positive. That's because your protons are still there. This should not be anything new. This is exactly what we called the definition of a cation back in previous chapters. If you become positive, you're going to be a cation. So in this case, you're just going to be a positive oxidation state, but it's basically the same thing. And if you're going to become negative, it's because now you own more electrons than what you started with, and that was really the definition of an anion. So even though charge is not exactly oxidation states are the numbers needed in order to achieve an overall charge. They're not real charges, but we can almost imagine them to be the charged feelings of atoms inside a molecule where there's lots of bullying going on here or there. So when we come back, we're going to start to show you that there are shortcuts. If you look at this one example first, though, there is a uniqueness to oxygen here, whereas if you notice these electrons that are being shared here, there's equal bullying because we got 3.5, 3.5, and 3.5. When that happens, you have to split the electrons. Oxygen starts with 6 and it ends with 6, so it has no charge. Oxygen starts with 6, it ends with 5. It's going to be a +1 charge. Oxygen starts with 6, it ends with 7. It's going to be a -1 charge. So when you're sharing with yourself, you have to share equally. And that's what we're seeing here for ozone, the molecule, which is just another example of oxygen doing something that it may not want to, but because it's attached to itself, it has to. So the biggest limitation of these issues is to draw Lewis dot structures. You may have forgotten how to do that because we haven't had to do that for several chapters now. But there is a shortcut, and we're going to be showing you that very soon. So we'll show that separately in the next video. See you then.